Welcome viewers. What happened till now is we did everything which was called as ordinary differential equations, and if you have noted, we have all total differential operator like dy upon dx. Now what we begin with, the title shows, is partial differential equations, where we will be having all that is called as partial differentiation. All basic techniques, fundamentals, process, nomenclature, everything will be borrowed from the partial differential calculus, or partial differentiation as a method is very important method in all advanced mathematics. Mostly we are dealing with this. We will be starting with formation of partial differential equation, and then we will be coming to partial differential equation of the first order, like what we have in ordinary differential equations as well. The prologue is important. I try to make it very comprehensible to you all. If you read it very carefully, what I have told you will be repeated again. We have studied differential equations where there was only one independent variable. That is the first definitions we are all taught at the earlier classes, and at the time when we are taught partial differentiation. This line is very important. That means all we have done up to now is y is equal to fx type of a relation. Now we study the differential equation involving two or more independent variables, meaning thereby we will be starting with z is equal to function of x and y, where x and y are taken as the independent variable and z becomes a dependent variable, like what we have in y is equal to fx relation. These notations are all known to us, very fundamental notations. The P, the Q, the R, the S and the T. Notations are simplified, illustrated to give you a reminder of what we have done in the very basic classes that we have been taught, the partial differentiation. P denotes partial differential of z with respect to x. Remember one thing, if you are differentiating partially with respect to x, rest all variables occurring in are to be treated constant. If I am doing with respect to y, rest all the variables except y are to be treated as constant. Then R is the second differential of P, so that I can write that d2z dx square is nothing but dp upon dx. We'll have it later. S is the cross derivative double second order. So we say it d2z dx dy. We are aware of this, we know this, we are familiar with this notation. T is the second partial derivative of y, in other words of q, and so you look into here. All these relations, what we have named as P, the other we have taken as P, Q, R, T and S are like this. As we were discussing, dp upon dx will be called R, dq upon dy will be treated as T, dp upon dy and dq upon dx all will be equal to the second order cross derivative relation that we had in the preceding page. An equation involving x, y, z, the partial derivative of x, the partial derivative of y, and similarly other terms are called as partial differential equations in x, y, z. If there is another variable x, y, z, w, then the whole sentence can be replaced by the other sentences and phrases. A general equation of the first order in x, y, z is written as this. It shows equation 1, shows that the function of x, y, z, p and q is the same as dz dx and dz dy, all are equated to 0, is called a partial differential equation, is called as linear. That means from equation 1 we come to the second part and saying that a partial differential equation is called linear if all the derivatives appearing in it are of the first degree. This particular phrase or this particular Definition is the same that we have studied in ordinary differential equation involving complete differential coefficient or total differential coefficient. General linear equation of the first order xyz is written as pp qq is equal to r. One is a small p, another is capital P, q and capital Q and r on the right hand side. We give meaning to it. P, Q, R are functions of x, y and z. 3 can be together, 2 can be together, or only 1. So, they are the functions of x, y, z, p, q and the right hand capital R. What we want to do is to study differential equation, of course partial, is formed. That means, how do we form a partial differential equation is a very important section that we are dealing with this. There are two methods, as you can see. The first is by the elimination of arbitrary constants, and the second that we will study is called as by the elimination of arbitrary function. We begin with number 1, and we will give a very small proof of this elimination of arbitrary constants. And mind it, we also try to give you certain illustrations, examples, the numericals where you can find how this theory or this concept is implemented there. So, we suppose the same thing that we have in equation number 2, that there is an equation given as f x y z a b equal to 0. That means function of this is equal to 0 given by equation 3. We say that is a function relating to x, y, z and a b are constant. So, this is in equation 3 is a function, a b are purely constants. In order to eliminate, because we are doing elimination of the arbitrary constants, they are not fixed constants. We need two equations. Naturally, a and b has to be eliminated, something like simultaneous equation x and y. We want to find the value of x and y in earlier classes. Similarly, we have here, we will be eliminating a and b, and we should have two equations. To obtain such, that means to obtain these two relations, we regard x and y as independent variables and differentiate one partially. We get this. All the other functions are taken constant. So, this equation df dx plus df dz dz dx equal to 0. This must be appearing to you to something familiar that we do in earlier classes as well. We come to equation 4 and 5 from the same. In place of all these notations which we have discussed right at the beginning, I replace them. Equation number 4 reads as df dx df dz p. P means partial of z with respect to x. We substitute, becomes equal to 0. The other is equation number 5, and you will notice that df dy df dz q is equal to 0. Q is dz dy, meaning thereby what we have differentiated, where 4 is obtained by treating y as a constant and taking z as a function of x. Very important to note these two lines. In this particular thing, from equation number 3 that we have obtained, 4 is this process. 4 is obtained by treating y as a constant and taking z as a function of x. Remember, we do not take z as a constant as well. We will have to take z as a function of x. So, it becomes dz dx. So, we can expect that when we will be differentiating again the fifth equation, we will be keeping x constant however, but we will have to take z as a function of y. We will see it how it happens. X is kept constant and z is taken as a function of y to obtain 5. So, 4 and 5 are obtained from equation 1 like this. From 3, 4 and 5, two constants a and b are eliminated. Two equations and two variables are to be eliminated. Those variables in this particular case are known as constants. So, we eliminated a and b by this sixth equation. This is a partial differential equation of the first order. I have given you a note here. We may see equation 1 that we have started with. very important thing. If there are more arbitrary constant like a, b, c, d, or a, b, c, for example, 3 instead of 2, the number of independent variables, then we obtain a differential equation of higher order, obviously. The differential equation which we have observed, naming it 1 and then we came to 3, are of a function x, y, z, a, comma, b. But we can write it x, comma, y, comma, z, comma, w, a, comma, b, comma, c. There will be 3 constant, everything is arbitrary, and 3 variables, instead of which we will have x, y, z and w as well. So that is called as differential equation of partial character of higher order. The second method, of which I hinted a little while ago, is the elimination of arbitrary functions, meaning thereby if there is an equation given as equation number 7, where you can notice that it is a function of u and v equal to 0, we consider this is a function of u and v, where u and v themselves are functions of x and y and z. And note it very carefully. We have said that we consider a function phi u v is equal to 0. I am drawing your attention because we are going to use here a very important name with which we are certainly familiar. So what this line indicates is that there is a relation giving a function in u and v, but u also is a function of x and y and v is also a function of x and y. If that is so, then differentiate 7 partially with respect to x and y, we get, this is completely a partial first order relation. We get this relation d phi du, du dx and du dz into dz dx, and then we have d phi dv equal to 0. We simplify d phi du, and instead of dz dx, which you can see here, dz dx, I have substituted for it the p, and here it is, you can make it this one. I have substituted again p for this particular thing. dv dx, this one is the same as this calculation or this calculation, so du dx. This du dx is straightway from here. This dv dx coming over here is without any change to this, gives us this equation number 8. We go a little further. Now we are doing it with respect to y, and so we got this result, that is equation number 9. What is next is important. We eliminate d phi du and d phi dv, or in other words, partial derivative of phi with respect to y and partial derivative of phi with respect to v from 8 and 9, these two big relations, and we happen to obtain this relation. Everything p and q are classified, we all know. du dx, dv dy are appearing as such from that relation, and this particular thing can be written as pp plus qq is equal to r. Very simple. P is a function of x and y and z, q is also a function of x and y and z. This, what we have as a small p is nothing but dz dx, and this q, as you have seen in equation 9, is dz dy. R also is a function of x, y, z. So I have given here, please see equation number 2 as a reference. In other words, I have given you the whole thing, how pp plus qq equals to r results into this. P is all these. This is very important to remember in equation 11, same thing is in equation 12, the same thing in equation 13. This partial derivative of uv in numerator on the right hand side, we will read it like this: partial derivative of u and v with respect to yz, partial derivative of uv with respect to zx, partial derivative of uv with respect to xy. If you note it very carefully, it goes like something cyclic order, yz, zx, xy. So, I do not think that it will be much difficult for us to remember every time. We come to next now. From 7 we obtain 10, that is a linear partial differential equation. Linear partial differential equation from 7 is an important note, therefore I bracketed, kept it in a box. You read it. If the given relation between x, y and z contains two or more arbitrary functions, then the resulting partial differential equation will be of higher order. The same thing, the same note that we have read when we were doing the other part, where we have done a formation of a partial differential equation by the elimination of arbitrary constants. Same thing. The elimination process remains a little different. As I was telling you, and I believe this will be very useful for all of us to know what we have learned and what we have studied and what we have read under these two boxes that we have taken, or under the process that we have written equation number 7, 8, 9 and 10, and then 11, 12, 13 are given here. The first question is, or the first example is, from the differential equation we are to derive any differential equation by eliminating a and b from this relation. This is a given equation, z is equal to ax plus by plus ab. What we do is we write down the first equation given, that is z is equal to ax plus by plus ab, and then differentiate it partially with respect to x. Which equation? This one. We come to 15. Look here, this is dz dx partially, keeping y constant now, and then ab being constant will have 0. So, by because of this will be 0, and so ax will give you only a. In place of dz dx by notation, I can put p is equal to a. That comes to give us the equation 15. And when differentiated partially with respect to y, the same thing happens here. Differentiating partially with respect to y, we mean keep x constant. Going back to equation 15 or equation 14, we have this becomes is equal to, and for this again, this dz dy where is written as q. The first notation that we are familiar with now, putting 15 and 16 in 14, we obtain, in 14 means in the given relation that we have, z is equal to px plus qy plus ab. We have removed ab. We have found the values of a and b, substitute here, and the required first order partial differential equation results as equation 17. We come here now, form the partial differential equation by eliminating h and k from, almost the same thing. So, we can make it equation 18, and then we have equation 19 derived from equation 18. The given is very simple. We have differentiated partially with respect to x and we get 19, and then we have differentiated with respect to y, and that results into equation 20, as we have done in the previous illustration 1. We eliminate h and k. They are obviously constants from equation 18, 19 and 20. What we obtain is equation 21. You do not have hk here. That means we have eliminated the constants, arbitrary constants, and therefore we obtain a partial differential equation of the first order. Another interesting, this is an ellipsoid, if you remember, x square upon a square, y square upon b square plus z square upon c square is equal to 1. We write the given equation as 22. We differentiate same, we do not change anything, any concept. With respect to x, taking z as a function of x, this is the new thing that we bring here. We are differentiating partially with respect to x, however, y is to be treated as a constant, but z has to be taken as a function of x. That is when we are doing with respect to x partially. What we get is this, 2x upon x square, because it was x square upon a square, so we get this. Y is constant, so y square upon b square goes to 0. And then we have the z comes at dz dx. We rearrange, simplify, get 23rd equation. Similarly, we are doing with respect to y, but remember, keep x constant and z as a function of y, we get 24. Now differentiate 23 with respect to x and 24 with respect to y. So we get 25, 26. Now the differentiation is not that difficult for us. We know how to differentiate partially. And from these 23 and 25, there are two pairs if you notice, 23 and 25, 24 and 26th equation. We will write such. We have this relation and we write 27th from 23, 25. Minus zp plus xp square plus xzr is equal to 0. And similarly from the other pair, 24, 26 equation, we obtain this result. That gives us the equation 28, we numbered it as, is minus zp yq square plus yzt equal to 0. This is a second order differential equation. If that is so, then we have shown that how the arbitrary constants are removed and we get a second order differential equation. In the first two example, number 1 and 2, we have shown or we have come to understand that how we eliminate a and b to get a first order differential equation. Now what we do is the second order differential equation. Now we are removing the arbitrary function from this. We differentiate partially given equation with respect to x and y, getting 29 and 30. Divide them, very simple. We get 31. This is a linear equation of the first order. This one, linear equation of the first order, Pp Qq is equal to R, to remind you. Linear equation of the first order is the another part that we want to do here. This section is devoted to the study of the equation Pp plus Qq is equal to R. Very interesting, very important, again called as Lagrange's linear equation. Any person solving linear differential equations the first order without having this name in his mind, without having this linear equation properly solved, understood, and after spending some time to make it easier, we cannot proceed on this. In the preceding section, we observed that the above equation is formed by the elimination of an arbitrary function. Equations numbers are given. In that relation, do you recall that we had phi uv is equal to 0, u and v are functions, and then we said u is a function of x and y, v is also a function. Same thing we are referring again. Therefore, it is preferred that the general solution of linear equation of the form 2, the above must be of the form 7, and so it carries some meaning. So equation equivalent to the linear, we want to explain that the linear equation given by 32, which we have read earlier, is equivalent to this and this, 34 and 33, is the solution of 32 or of the equation 2. Let me differentiate 34 partially with respect to x and y, and we obtain these results, very simple. Then we have the relation q is equal to minus du dy and minus du dz is also very interesting. We are substituting 37 and 38 in 32. We get this relation p du dx, q du dy, r du dz is equal to 0. If you recall this equation, this one I am talking about, finding this equation 39, or by substitution of this equation 38, is almost the same as equation 33 if you look back. Very simple equation. They are called as linear differential equation partial of the first order, because you look here and in place of this we don't have any second order differential. So these are the classifications that we can borrow from the partial differential equation of the first order. Linear, the name given to it is very clear to all of us. What we have done in this lecture is very simple, is very elegant after we have done the first part of it, meaning thereby so far we have considered what we call as a total differential dy upon dx, and we have framed differential equations of ordinary type which we called as ODE, meaning thereby ordinary differential equation. In this particular lecture what we have done is the partial differential equations. It is classified into two things. In the first, we have given formation of a partial differential equation. The partial differential equations are formed by two methods as we have described. The first one is by elimination of arbitrary constants. As you have seen, we have named them as a small a and small b. In the second part, we have given some illustrations, some examples, and we have tried to solve them in a very easy fashion to make you reasonably understandable, is by eliminating arbitrary functions. Though both looks almost the same, but you will appreciate the excellent use of partial derivatives which we have studied, and I told you during my lecture that recently that P, Q, R, S, T has to be remembered by heart, and they are very easy. All are first derivatives of partial order, but one thing, S is a cross second order partial derivative, whereas P and Q first order, R and T second order with respect to Y. And another very important thing, that while solving these partial differential equations that you have seen, you have noticed one great thing, that we differentiate partially with respect to x, of course keeping y constant, but then there is a line which we have drawn, little different from what we have studied earlier. Differentiate something partially with respect to x keeping y constant, but z has to be taken as function of x. The second part of it, which probably we have when we were dealing with equation 23, 24 or maybe 25. We had differentiated the whole thing with respect to y. This time we kept x constant, and then we proceed to have the z as a function of y. These two has to be remembered. Then we have the partial differential equations converted into linear differential equations. Very easy. PP QQ is equal to R. We will continue this, lecture, and in the next part of this we will discuss what we understand by the linear equation of the first order that we have introduced here. In the second part of this lecture that we will have next time, we will try to understand what we mean, the details and the concept of mathematical analysis therein. Well, once again thank you for the attention, and get prepared for learning more about partial differentiation. Thank you.